A large deep bath contains molten steel, the surface of which is in contact with air. The oxygen concentration in the bulk of the molten steel is 0.03% by mass, and the rate of transfer of oxygen from the air is sufficiently high to maintain the surface layers saturated at a concentration of 0.16% by weight. The surface of the liquid is disrupted by gas bubbles rising to the surface at a frequency of 120 bubbles per meter squared of surface per second. Each bubble disrupts and mixes about 15 centimeters squared of the surface layer into the bulk. On the assumption that the oxygen transfer can be represented by a surface renewal model, obtain the appropriate equation for mass transfer by starting with fixed second law of diffusion and calculate A. the mass transfer coefficient, B. the mean mass flux of oxygen at the surface, and C. the corresponding film thickness for a film model, giving the same mass transfer rate. The diffusivity of oxygen in steel is 1.2 times 10 raised to negative 8 meters squared per second, and the density of molten steel is given by 7,100 kg per meter cube. If C' is defined as a concentration above a uniform datum value, therefore partial derivative of C' all over partial derivative of T is equal to D times partial derivative squared C' all over partial derivative Y squared. So that leads to the boundary conditions that when So this equation is most conveniently solved using Laplace transforms. The Laplace transform of C' of C' is given by then the partial derivative of C' all over the partial derivative of T is equal to the integration from 0 to infinity e raised to negative st partial derivative of C' over partial derivative of T dt. That leads to the equation since the Laplace transform operation is independent of y, therefore, taking Laplace transforms of both sides of the equation, from which C' is equal to AE raised to square root of quantity P all over D quantity Y plus BE raised to negative square root of quantity P over D quantity Y. When y is equal to infinity, C' is equal to 0 and A is equal to 0. When y is equal to 0, C' is equal to C'I over P and B is equal to C'I over P. Inverting the partial derivative of C' all over the partial derivative of y is equal to negative C'I all over square root of t times 1 over square root of pi t times e raised to negative y squared all over 4 dt. Therefore, the mass transfer rate at the surface and the average rate of mass transfer in time t is given by taking 1 meter squared of surface, the area disrupted by the bubbles per second is 120 times 15 over 10,000 is equal to 0.18 per seconds. Therefore, the average surface age duration is equal to 1 over 0.18. That would be equal to 5.55 seconds. That leads to C'I is equal to 0.16 minus 0.03 all over 100. That would give us 0.0013 kilogram O2 per kilogram steel. And then 0.013 all over 32 times 7,100 is equal to 0.2885 kilomole per meter cube. Therefore, we can now solve for the mass transfer coefficient equals 2 times square root of d all over pi t. That would lead us to the equation 2 quantity 1.2 times 10 raised to negative 8 over pi times 5.55 quantity 0.5. Then that would give us the answer 5.25 times 10 raised to negative 5 meter per seconds. Then, the mean rate of transfer NA is equal to 2C prime I, quantity D, over pi T, quantity raised to 0.5, is equal to 2 times 0.2885, quantity 1.2 times 10 raised to negative 8, over pi times 5.55, quantity raised to 0.5. That would lead us the answer 1.51 times 10 raised to negative 5 kilomole per meter squared seconds. Then the film thickness L is given by NA is equal to quantity D all over L, quantity C bar prime I. And L is equal to quantity 1.2 times 10 raised to negative 8 times 0.2885 all over quantity 1.51 times 10 raised to negative 5. That would lead us the answer 2.29 times 10 raised to negative 4 meter or 0.23 millimeter.